Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be continuing Chapter 17 on classification. And we're starting by using the discussions of cross-validation and prediction accuracy from the previous video with the Fisher's iris dataset, the overused dataset in statistics. So we're going to illustrate cross-validation on the Fisher's iris dataset by first using a training and test dataset, and then we'll also use the jackknife method. So we have 150 observations in the dataset, 50 observations for each of the three subspecies of iris, or varieties of iris, setosa, versicolor, and virginica. And what we're going to do is we're going to randomly partition the data into a 50-50 split of a training set consisting of 75 flowers and then a test set for 75 flowers. We're going to pull 25 flowers for each of the three varieties of iris. So let's start by performing that 50-50 split. I have one additional comment which is really important here. So regardless of the split that you use when you perform cross-validation, at the end of evaluating how well your classification is likely to perform, you should always use all of your data set, so combine all the data together to create the actual rule for classifying future data set. This K-fold, cross-validation, and jackknife, and so on are all just methods to evaluate the classifier, but of course you'll always use all of the data in performing and generating your actual classification rule. All right, so here's the Fisher's iris data in the dataset iris. It's got the four features that we care about and species, and we're going to use the plier package to split the data up by species. And then for each species, we're going to apply this function, which is going to randomly divide the data set in half, and then we'll combine all of those at the end with labels that are either training or test. The way this function works, in fact, maybe just show what the output is. If we create a table of the species and whether they're in the test set or the training set, here's the result. That we've got 25 observations for each variety in the test and the training set. So the way that I've done this is in the iris data, I've split the data set into three groups based on species, and for each group, which is now the data set for each group is called X. I'm going to count how many observations there are. Okay, so there's 50 in n row X. And I'm going to sample integers, sample.int. And there's going to be the numbers from 1 to 50. That's what n row specifies. And the sample size that I'm going to draw is the number of rows divided by 2. So that's half of the observations. And in case I were doing this with a random set of data that didn't have 50 observations in each, I'm going to round this to the nearest integer. Just a minor detail. And this is going to sample without replacement, meaning the indices that I select from the numbers 1 through 50 won't repeat in the data set. I sort them, which is not really that critical. Oh, actually this would just print them out. Because this doesn't assign this to anything. I think this was me just testing that this was working. Then I'm going to create a new column called test, and I'm going to assign all of those to equal train initially. So there's the 50 observations in X are all going to be labeled train, and then the indices that I sampled, I'm going to label test. So that gives me the 25. I start off with 50 training, but then I overwrite 25 of them with test. I set that as a factor variable. This also would just print it out. It's me testing them out. Within the context of this function, it doesn't return output to the screen. So these minor details for of me writing the function and testing it out are hidden. And then I return x, which is the entire data frame, back into iris. So I've effectively appended one column to the iris dataset called test that has this train test label. And if I look at a summary of that test column, I've got 75 in each, more specifically 25 for each species. Let's plot the dataset, and I'm going to effectively use this throughout. A subset of the iris dataset where the test label is train, and then down here the test label is test. So I'm going to plot both the training set and the test set, and because these are randomly sampled, we should see effectively that these two distributions are very similar to each other. We see that the orders of the box plots are the same for the two halves. The marginal density plots on the diagonals look relatively similar. You can see some variations. For example, this green hump on the right in the test data set is not quite as humpy on the training set on the left, and that's just because of the random sampling. If you actually run this code, you'll probably get a slightly different result, because I didn't set a random seed here. So if I were to run this again and again and again, I would get different partitions of the data set. All right, so let's take a look at using the training set. We're going to basically look at the training set a bunch, and then we're going to ultimately test the classification on the test set. So I'm going to use the partition matrix for species based on the 4 features of petal and sepal length and width on the training set, and we're going to plot that matrix, and there it is. For some pairs, and so I would think of this matrix as simply an exploratory tool of how well classification is likely to go if you were to use the variables or features pairwise and not looking at them all together. Certainly sepal length and sepal width, we have a classification error up here of 0.22, very high. So, I should point out one more sort of annoying thing in this data set. We have 3 varieties. We have Setosa, versicolor, and virginica. And versicolor and virginica both start with V. So V is what's being plotted. The only way really to distinguish which group each plant belongs to is whether they were classified correctly or incorrectly. So all the black V's in the white space are correctly classified, and those are probably virginica. And then the red V's in the magenta shaded areas are also, did I say the right thing? Let's see, I think these are probably versicolor, the black ones in the white space, and then these red in the magenta are also versicolor. Those are being misclassified. Anyway, some of these are giving rather low misclassification rates, error of 4% or 5%. Effectively, once you start including petal information, your classification error goes way down. Let's look at the linear discriminant analysis using all 4 features on just the training set. The prior probabilities for each group are 1/3 by default, and also in actuality, because we do have equal sample sizes of each. And we have the group means for each of the 3 varieties. But here's the linear discriminants, basically positive for both sepals and negative for both petals, and that this linear discriminant 1 accounts for most of the discrimination ability, with linear discriminant 2 being basically ignorable. If I write those out as equations, this is what they look like, and effectively, as the sepals get larger and the petals get smaller, I'm basically interpreting the signs of the coefficients. We have 2 positive ones for sepal length and width, and we have 2 negative signs for petal length and width. it's in that direction where as sepals get larger, petals get smaller, or vice versa. That's the ability, that gives us the greatest ability to distinguish between these three varieties. If we show this data on the linear discriminant scale, either looking at one dimension at a time or both dimensions, so each of these axes is linear discriminant direction 1. We have setosa up top. Let me make this a little bit bigger. We have setosa up top, versicolor in the middle, and virginica in the bottom. And you can see how well along that one axis these separate. There's very little overlap even between versicolor and virginica. And over here is linear discriminant axes 1 and 2, and you can see number 2 doesn't offer a lot in terms of discrimination up and down. All right, finally, cross-validation. I'm going to start off by doing the jackknife, which was the n-fold leave one out cross-validation strategy. And the way you get that is simply by adding the argument CV for cross-validation equals true in the LDA function. So this is for the training set, and I'm going to use all the variables, and I'm going to put that into lda.iris.cv. And now I'm going to create that same classification table that I made previously for the turtle shells when we were classifying males and females. All right, so we've got a species column which gives the true species for each plant. We have the classification plant column. We have the error, which is going to be built on below, and then we're just naming the columns here. And in particular, we have posterior probabilities for all three species. So this is going to be post setosa, virginica, setosa, versicolor, and virginica. All right, and then I add some errors, stuff to the error column here. Let's take a look at the summaries for this data set. If I create a table of the training set where I use the species as the rows and what it was classified onto as the columns, and look at those frequencies, we can see that 25 of the setosa were classified as setosa and 0 were classified as the others. So that's perfect classification for a setosa. No surprise, because setosa is miles away from the other two. For versicolor, 23 were correctly classified with 2 misclassifications. And for virginica, we had 24 correct classifications with 1 misclassification. So there's a little bit of misclassification for these versicolor and virginica, but pretty low rates overall, from 4 to 8%. If we look at that same table but look at the row frequencies, we can see the 8% error for versicolor and the 4% error for virginica. The diagonal gives the proportion of each that were correctly classified, and the total proportion correctly classified are the diagonals of the table that are for the entire table proportions, not just the row proportions. And finally, the overall error rate is just 4%. So that's not bad. 1 in 25 plants we would expect to be misclassified. And more specifically, we don't really expect setosa to be misclassified, but there'll be a little bit of misclassification between versicolor and virginica. Finally, we've assessed how well we expect our classifier to work from our training set. Let's see now how it performs on the test data set. So predict is going to use the LDA, the linear discriminant analysis model that we developed in our tests or in our training set, and now we're going to predict some new data that is coming from our test subset, and that is going to be our predictions for the iris data set. I'm creating the same classification table as before, and now the true species are from the test set, the classifications are from our prediction object, and so on. And here is the classification table. We have the true species, setosa. We have the classified species, Setosa. We have the error column, and right now there's nothing in there because all of those are correctly classified. And then we have the probability of Setosa, versicolor, and virginica based on that Mahalanobis distance probability that we defined in the previous video. And for Setosa, because it's so different than the other two, you can see effectively we have probability 1 for all the Setosas. When we get down to versicolor and virginica, so here's versicolor, and you can see how high the probability is for the versicolor for most of these. In fact, all of them are all very high, surprisingly high. No misclassifications for versicolor. And for virginica, I'll scroll up just a little bit. Now the third column, the probability of virginica is quite high. We do have some versicolor probabilities that are basically non-zero, but none that are greater than they are for the virginica. So all of those were correctly classified. This happens to be a remarkable result that we performed perfectly on the test data set. This basically never happens. Okay, don't expect this to happen for your data. In fact, you often expect that the classification on the test set is slightly worse than on the training set. If we look at the classification tables, we see perfect classification along those diagonals. So these summaries are not really interesting in this case. And so this worked remarkably well. Do not expect such nice results on all classification problems. Usually the error rate is slightly higher on the test set than the training set. So one comment here is to help you think about the difference between performing the hypothesis test using multivariate ANOVA versus doing classification. So say you had two groups, or in this case 3 groups, that were significantly different from each other. Why does that not necessarily translate into having accurate classification? So the main idea here is that when you are performing multivariate ANOVA, you're only asking the question, are the means between the two groups different or not? Or the many groups. Are those means different? And that doesn't ask about how the distribution of the data actually are, or the distributions of the populations. You know, just as a mental experiment, basically because I don't have a good image to point to. Actually, let's see. So I'm down to 474. If we look at this, example, here we've got 2 subspecies, and the means. You know, you can sort of point to where the means are. They're in the center of these ellipses. And those means are fairly different. If you had a sample size of, say, at least 10 or so for each subspecies, you could probably distinguish that these 2 means were different. However, the population distributions overlap substantially. There's maybe about a third overlap in terms of the area for each of these ellipses. So we can expect maybe about a 16% misclassification rate in this example. So there's a distinction, of course, between the standard error of the mean, so how much uncertainty you have in the mean, versus the standard deviation of the entire population, which says how much spread there is in the population. And when you end up with that overlap gives you a challenge when you're doing classification. All right, so the next step in this video is stepwise variable selection. So we've seen stepwise model selection for multiple regression, where we ask which variables are important to have in a regression model to help predict the response, conditional on the other predictors that are also in the model. And we can ask that similar question when we do classification. effectively we're asking which variables in the model help you when you perform classification, and which variables can be ignored. And stepwise is one strategy to help you select among variables. In the Fisher's iris dataset, we only have 4 variables. It's not very much. There's a classification problem I will probably introduce you to in a homework or an in-class assignment, which has something like almost 100 possible predictor variables. And so selecting from those would not be something you'd want to do by hand. All right. So as in multiple regression, we're going to have some starting model, and then we'll have some rules that are defined in the step class function for including or removing variables, and then it will stop when it can't find additional improvement by either excluding or including variables. And of course this can be very sensitive to the starting model, so where you start can affect where you end up, and we'll see that immediately with the iris dataset. So here is in the KLA-R package the step class function, and we basically put in the formula for the classification variable for species, the 4 features we're interested in. Here's the dataset. We're going to use the linear discriminant analysis method for performing classification, and we're going to, in this case, do backward selection. And the improvement here is we're going to stop if improvement is less than 1%. So that is the amount improvement that we can tolerate by removing a variable. Basically, we want to simplify our classification model, perhaps, if we want to point specifically to which variables are responsible for good classification. And we're willing to take a 1% decrease in our classification accuracy if we can simplify our model by 1 variable. So that creates a balance of 1 variable is equal 1%, or it has to be worth a little bit more than 1%. So it's going to perform stepwise. Here's the comments after running this function. It's performing stepwise classification. It's using 10-fold cross-validation using LDA. We had 150 observations, and we have 4 variables and 3 classes, and we're going direction backwards. I love this in a function, to be able to give the output to help you verify that, in fact, what you specified is what the function is running. And the stopping criterion is that improvement is less than 1%. So we start off with, we have a correctness rate of 98%, starting with the full model. The starting variables are all 4, and they go off the page here, but they're all 4. And it took about 1/4 second to run this. And if we plot the results, I'll scroll down and plot those results. Here's the starting model. It had an estimated correctness rate of 0.98, I think, and there it is. And it didn't go anywhere. Basically, the final model is the same as the starting model. Now, we couldn't drop any variable without losing more than 1% accuracy. Okay, we're going to come back to the plot on the right. I also performed this using forward selection. So it's going to start with an empty model and then go forward. And when you start with an empty model, the first variable it adds is petal width, and you get up to 96% just by adding petal width. So that's pretty remarkable. With 1 variable, you get 96% correctness. And then it ended. So that's our final model then, petal width. So we went from a 0 correctness up to a 96% correctness with petal width, and then we couldn't find a single variable that increased our accuracy by 1% or more, and so we stopped. Effectively, once you have petal width, each additional variable adds less than 1%. So that it wasn't enough to make that model more complicated. So these are quite different ending models. In this case, we started with backward selection and we didn't go anywhere. We ended with the full model. Here we started with an empty model and only included one term, petal width. If you change this improvement amount to say 0.001, so you have to increase 0.1% or so, you'll get different answers. And I think the main point here is because the results can be really sensitive to your choices. Perhaps try several of these. Try it going forward and backwards and see what the results are. And then as a human who's smarter than a computer, make a decision. Okay. I think the only other thing here is that there's times when you've got right, formula. So backwards formula. You know what? I think that there's some output here that I see. So when I specified the step class function here, I put that into step.iris.b. The b was for backward selection. And when you print out the formula, that's the final resulting model. So, and that's the formula that in this case was used here. So that was the input formula. It did backward selection, and the final model is in this formula term. When we did forward selection, which I called .f, and I look at the $ formula value, this is the final model here, petal width. So the reason I bring this up is because we can use this formula that's stored. We can also define it ourselves. It's pretty easy. You can use the function formula with parentheses to define a formula and assign it to an object. So here's the LDA. This is the LDA after performing backward selection. So if we want to look at the LDA results from the model that we arrived at, we can use LDA and just pull the formula right from our step class object. So there's all the output, and this is the same output we've seen before because we did LDA with all 4 variables before. The final comment here is it sometimes is useful to define the step class syntax using separate data frames rather than a formula. In particular, here we have the classes, which are stored in, it's the species stored in the 5th column, and that's here the 2nd argument. And then the data, the 4 features, are these first 4, and I'm putting that here. So when there's lots of different data columns, and it's maybe easier to reference them by column numbers rather than, you know, if you had 100 columns, you wouldn't want to have to type all of those variables out. And so it's much more compact to simply say, you know, the first 100 columns or something like that. And you can say this is the data, first argument, second argument is the classes. So that's a shortcut that you may find helpful in a homework assignment, for example. I will come back in the next video and we'll look at the final example where we will look at admissions data for a university, and we will use unequal prior probabilities of class assignment, and we will also look at the quadratic discriminant analysis function, which allows us to not have equal covariance matrices for the 3 groups or for the classification groups.